Hello friends, now we have been discussing about oscillations, then basics of oscillations, then differential equations of forms of differential equations of simple harmonic motion. Uh, we need to figure out what is the displacement and velocity and acceleration of this particle performing simple harmonic motion. But then before that we need to understand a few concepts. Okay, now when I say this pendulum, okay, and it is that bob is here. Okay, now this string is vertical, if even if it doesn't look like here, just you have to forgive me for that, and it moves here and then it moves here. Okay, so whatever distance it moves towards right, same distance it moves towards left, correct? So it's going to be like this and then back to this, correct? So this is my mean position. It moves like this, comes like this, and comes back over here, and it continues. Okay, does at any point of time this bob move any distance more than what this position is? No. Whatever initial displacement that I have given, okay, and I release it from that point, it will move the same distance all the time. Okay, and here I am assuming an ideal simple pendulum, number one. Number two, there is no air resistance. So when I give some initial displacement, this simple pendulum is going to oscillate forever, which is practically not possible, but then we are assuming that, because we are not going to observe its oscillations for a long time. Okay, the time of observing maybe as small as 1 minute, right? Now but then the thing is, there is some maximum displacement on either side, and then this maximum displacement on either side, it is called amplitude. Okay, now this is, let us say x is my initial position, then A here and B here. Okay, A is the extreme position towards right and B is the extreme position towards left. So how does one oscillation get completed? So it would be from x to A, then A to x to B, and B to x. So x to A to x, A to x to B, and then B to x. So it is one complete oscillation towards right, mean, left, mean, and one oscillation is complete, correct? And then time taken for that is called period of oscillation. Okay, so amplitude is the maximum displacement from the mean position, time period is the time taken for completing one oscillation. Then what is frequency? It is the number of oscillations in unit time. So if a pendulum makes let us say 2 oscillations in 1 second, then its frequency will be 2, correct? So something called frequency here. So period is denoted by T, amplitude by, let us say, capital A here, and frequency would be N or F. N or F, any one letter you can use. Frequency is generally indicated by nu. Now what is this nu? It is Nu. Its pronunciation is Nu. It's a Greek alphabet. But then for simplicity we would be using N or F here. Okay, so that was about some basics that I wanted to underline over here. Okay, now let us move to what we have where we had left in the last video. Now that was something like this acceleration is equal to minus k upon m into x. Here x is the displacement and a is the acceleration, k is the force constant or spring constant, m is the mass of the object or mass of the vibrating body. Now I am going to substitute k upon m. Okay, this k upon m I am going to expressed as omega square. This omega is again a Greek alphabet. It is something similar to what you have learnt in motion in circle. Okay, over there this omega was angular velocity. Okay, here we are going to call omega as angular frequency. Now what is angular frequency? I'll be discussing that at a later stage, but then for now you can take this omega as angular frequency. Omega is equal to root over k upon m, and that is called angular frequency. So that is when I say angular frequency, it would be angle upon time, correct? So its unit would be radian per second. Okay, so you just keep that much in mind at this point of time. Okay, now let us make use of this. We had that differential equation of SHM, and it was something similar to this, right? So I'm going to write here as my A is equal to minus omega square into x, correct? What we know so far is acceleration is rate of change of velocity, right? So I would say alright, now I'm going to clear this part so that I would be able to use this part as well as that part. This you don't need right now. So my acceleration is equal to dv by dt, correct? Now this I'm going to write as dv by dx into dx by dt. Now for more details on this calculus part, you can refer to my videos in the playlist calculus for physics, okay, and that would be mentioned in the description here. Okay, so now what is my dx by dt? Is it not my velocity, right? So I would say that dv by dx into v, correct, and that is my a, right? So can I write something like this? A dx is equal to v dv, correct? Okay, now what? Here now I have some differential equation here which I can integrate, okay, and maybe I would be able to get velocity here, right? So what is my acceleration? Is it not minus omega square x? So let us put it over here, minus omega square x dx is equal to v dv, correct? And I'm going to integrate both sides. Now this omega square, okay, this omega square, is it not constant? Omega is what? It is k upon m, and k is the force constant and m is the mass, which is constant. So k upon m is constant, omega square is constant, so I am able to take it out of the integral sign here, and what I get over there is minus omega square into integration of x dx, that would be x square upon 2, and similarly on the right hand side it would be v square upon 2 plus that, what is it, c? C is the constant of integration, okay? C can take any value, isn't it? We are talking about definite integral here, so that means we have to evaluate, right? We can't just leave it as it is. We can't just leave this whole equation as something plus c. We have to figure that out. It will be having some definite value to it, correct? How do we do that? So for that, we should have some boundary condition. Okay, when I say boundary condition, I would say, alright, just imagine this. Okay, the bob is pulled towards right, to your right. Okay, it is pulled towards right, and you leave it, correct? it comes to the mean position, but then again it keeps on moving straight, isn't it? And then it reaches the other extreme position, and then from that extreme position it is going to come back, isn't it? So can you say that for a fraction of a second, when it is at the extreme position, for a fraction of a second, the velocity of the bob becomes zero and it reverses the direction? Correct. It was, the velocity which was positive, it reduced to zero and it got reversed. Now it became negative, started moving in the opposite direction. So that means at my extreme position, my velocity is equal to zero. Correct. So, and what is my extreme position? Is it not the amplitude? When my displacement is equal to amplitude, my velocity is equal to zero. So at x equal to a, that is amplitude, my velocity is equal to 0. So let us put it here. So minus omega square into a square upon 2 is equal to 0 plus c. So that means my c is equal to this, correct? So why not put that c, value of c over here? So minus omega square x square by 2, correct, is equal to v square by 2 minus omega square a square by 2. Correct. Now what do? I take this on that side. So I can also cancel this 2 on both the sides. So my v square is equal to omega square a square minus x square. Correct. So my velocity is equal to root over. Now here I am going to get plus or minus. So I am going to get two values, positive and negative. So plus or minus omega root over a square minus x square. That is the expression for velocity of a particle performing simple harmonic motion. Now here I have these two values of velocity, and that makes perfect sense, right? Because when you are going towards right, at some particular distance from the mean position, your velocity is towards right. Okay, so if we take velocity towards right positive, then obviously velocity towards left is negative, correct? And now it reaches the maximum point, that point of amplitude, and again passes through the same point. Now at that time it is moving in the opposite direction, isn't it? So the velocity is negative with respect to what it was earlier, right? So that means the velocity, positive and negative values of velocities here, that makes perfect sense. Okay, and then again, if you substitute the different values of x over here, you would get that at my extreme position, that is my amplitude position, x is equal to a, over there my velocity is equal to 0, and actually that is what we substituted while evaluating the constant. But what about velocity at the mean position? So for that you have to substitute x is equal to 0, correct? So at the mean position, your velocity is going to be, you just put x equal to 0 here. So this would be root over a square. So that square root of a square would be a. So my maximum velocity, so V max, if I ever call it, it can be plus or minus a omega. Again, the same reason for the two signs, positive and negative signs for velocity, because it can be, when it passes through the mean position and it is moving towards right, okay, then the velocity is positive, and when it passes through the mean position and moving towards left, the velocity is negative, correct? So that makes perfect sense, and your maximum value of your velocity is a into omega, where omega is the angular frequency. Now in the same way, what is the maximum value of acceleration? Your acceleration is this, correct? acceleration. Now if you put x is equal to 0, that is at the mean position the acceleration is 0. See, the velocity at mean position is maximum, but then acceleration at mean position is 0, isn't it? What about acceleration at the extreme position? When the velocity is 0 at the extreme position, your acceleration is going to be equal to, I would write a max here, and that is going to be equal to, you just put x is equal to capital A there, so minus a omega square, correct? This is your maximum value of acceleration, correct? So acceleration is 0 at the main position and maximum at the extreme position. Velocity is maximum at the mean position and minimum at the extreme position. So that was about velocity and acceleration. In the next video, we are going to talk about the displacement, expression for displacement of this particle performing uniform circular motion, and then we will also be discussing how this velocity and acceleration, we call it simple harmonic motion. That means the functions that we are coming across here, they are harmonic. And what are harmonic functions? They are periodic functions, right? We will be discussing graphs of these functions in the next video. Thank you so much.